Okay folks, welcome to Chapter 3, Mass Relationships and Chemical Reactions, or, as it's more succinctly known, stoichiometry. In the previous chapter, we started talking about chemical reactions, mostly in the sense of classifying elements by certain basic chemical properties. Let's dig deeper. At the top of the screen right now, you have what's called a balanced chemical equation, which is a way of showing how chemical reactions take place. The reaction arrow separates the substances on the left, the reactants, from those on the right, the products. The reactants are the substances present before the reaction takes place, and the products are what they're transformed into as a result of the reaction. In our case, we're looking at the reaction of the elements hydrogen and oxygen to form the chemical compound H2O, better known as water. The subscript of 2 after H tells us that we're dealing with molecules containing 2 hydrogen atoms each, the default state of that element, and the same is true for the subscript 2 after O, the chemical symbol for oxygen. The chemical formula for water shows us that we have molecules containing 2 hydrogen and 1 oxygen atom each. There's also a 2 in front of both H2 and H2O in the balanced equation. This gives us 2 related pieces of information. On the microscopic or molecular level, it means that 2 molecules of hydrogen react with every 1 molecule of oxygen, and the result is 2 molecules of water. The G in parentheses after H2 and O2 tell us that these substances are in the gaseous state. The L in parentheses after H2O tell us that the water is in the liquid state. This molecular level understanding is easier to conceptualize in some ways, but it's not very useful for the amounts of substances on a human usable level. For that, we need to interpret the stoichiometric coefficients not as numbers of molecules, but rather as the amounts of moles of each substance. So on a practical level, we can say that 2 moles of hydrogen gas react with 1 mole of oxygen gas to yield 2 moles of liquid water. Remember, 1 mole is 6.022 times 10 to the 23rd molecules. A balanced chemical equation must conform to the laws of conservation of mass and the principle that chemical reactions cannot transform atoms of one element into atoms of a different element. To account for this, we need the amounts and types of atoms on both sides of the reaction arrow to be identical. For example, in the reaction between sodium metal and chlorine gas to form sodium chloride, the reaction is balanced with a coefficient of 2 in front of both sodium and sodium chloride. In case it isn't clear, there's an implied 1 in front of the chlorine here. Just like with the chemical formulas, stoichiometric coefficients of 1 are unwritten. Let's dust off a reaction that we used to demonstrate the law of conservation of mass in the previous chapter, the reaction between mercury 2 nitrate and potassium iodide to form the bright orange solid mercury 2 iodide as well as potassium nitrate. A quick note on some of the states of matter here. Lowercase s in parentheses indicates a solid, and the lowercase aq in parentheses indicates that the substance is in the aqueous state, which is the technical term for something that's dissolved in water. Looking at our equation, we can see that it's balanced. There is 1 mercury, or Hg, atom, 2 nitrogen atoms, 6 oxygen atoms, 2 potassium, or K, atoms, and 2 iodine atoms on both the reactant and product sides of the equation. When counting these, you need to take into account the numbers in front of any chemical formula, as well as any subscripts in the chemical formulas themselves, including any that come after parentheses. I strongly encourage you to verify the amounts of each element on this slide on your own. If you're having trouble, it's definitely possible that you misunderstood either how the stoichiometric coefficients or the numbers inside the chemical formula work. Especially if it's the latter, you'll want to brush up on what we're going through in the previous chapter. I'd be happy to walk any of you through the problem. If you're having trouble, just drop by my office hours or talk to me during or after class. So far, we've just seen examples of chemical equations that were already balanced. But how could you balance an equation on your own? Let's say you had the unbalanced form of the equation from the first slide, the reaction of hydrogen and oxygen to form water. The first step is to make sure that all the reactants and products are on the correct side of the reaction arrow, and that each has the correct chemical formula. So for instance, we need to remember that both hydrogen and oxygen are 2 of the 7 diatomic elements mentioned in the last chapter. Once you've got that part down, you'll need to find suitable coefficients to put in front of each formula to balance the equation. There isn't necessarily a way to do this that works exactly the same way for every single reaction, so you may have to do a bit of trial and error here. But the reactions you'll see in this class won't be terribly hard to balance, and the more examples you do, the easier this becomes. By the way, make sure you only try to balance the equation by changing the numbers in front of any of the chemical formulas. changing the subscripts inside the chemical formulas changes the identity of the chemical compounds, so you need to make sure that you don't do that. Once you have coefficients that balance the equation, you need to check to see if they can be reduced to a simpler whole number ratio. For example, if you'd gone through the process of balancing the equation we've been working with, it's conceivable that you might have gotten the version of the equation at the top of this screen. And indeed, this has 8 hydrogen and 4 oxygen atoms on both sides, so why isn't it considered correct? The answer is that the coefficients 4, 2, and 4 can all be divided by 2 to give a simpler ratio, 2, 1, and 2. Finally, the last step, as with any math or math-adjacent problem, is to verify that your answer is correct. Now that we know how to balance equations, I have some bad news. The molecular or molar ratios in a chemical equation are simple enough, but we don't set up chemical reactions in the lab by directly counting the number of molecules or moles. That's really not possible. Instead, to know how many moles or molecules of any substance we're dealing with, we have to weigh it. This means that we need a way to convert between the mass of a substance and the number of moles or molecules that represents. Enter the notion of molecular or formula weights. If we know what types of atoms and how many of each are present in a molecule, we can simply add the atomic weights together to find the weight of the molecule, also known as the molecular weight. And just like atomic weights represent both the mass of single atoms in AMU as well as the mass of 1 mole of atoms in 1 mole of a substance, the same is true of molecular weight. Let's take a look at a straightforward example, the molecular weight of hydrogen chloride. Each molecule of HCl consists of 1 hydrogen and 1 chlorine atom, so we just add the atomic weights of each of those together. The atomic weights of most elements on the periodic table are defined to a lot more decimal places than we need within reason, so in this example those atomic weights are just rounded to 1 decimal place. Adding 1.0 to 35.5, we get the molecular weight, which is 36.5. I left off the units on the previous slide because I want to re-emphasize the dual nature of what this value represents. A single HCl molecule will have a mass of 36.5 atomic mass units, but on a more practical level, that also means that 1 mole of HCl molecules will have a mass of 36.5 grams. And again, 1 mole means 6.022 times 10 to the 23rd molecules. Since any balanced chemical equation gives us information about molar ratios, but we can only measure mass directly, we need a way to convert the story that a chemical equation tells us into a version that includes information about mass. Here's where we get into stoichiometry. Let's say we have the generalized chemical equation here. Substances A, B, C, and D are generic placeholders here, not chemical formulas, and the lowercase letters in front of them represent the leading coefficients in the balanced equation. A reasonable question would be, I have X grams of compound A. How much of compound B do I need to react it with to make compounds C and D? This diagram explains how we can make this determination. We're starting with information about the mass of compound A we have. Molar mass is a conversion factor between mass and moles, so we can use it to transform grams of A into moles of A. Once we have things in terms of moles of A, we can use the molar ratio from our balanced equation to figure out how many moles of B will react with that amount of A. And once we have moles of B, we can use B's molar mass to convert that into the equivalent number of grams of B. Talking about it with a generic chemical equation gets pretty abstract, so let's look at a real reaction. At the top of this slide, we have the reaction that is used by a company like Clorox or any other manufacturer to produce household bleach. They take an aqueous solution of sodium hydroxide and bubble chlorine gas through it, which causes a reaction that forms sodium hypochlorite, bleach's active ingredient, and also sodium chloride in water. Suppose you were performing this reaction yourself, and you had 25.0 grams of chlorine to work with. How much sodium hydroxide would you need? The starting information in the problem is the mass of chlorine. We can use its molar mass to figure out the number of moles of chlorine, which allows us to use the coefficients in our balanced equation to figure out how many moles of sodium hydroxide are needed. Finally, with that information, we can use the molar mass of sodium hydroxide to calculate the appropriate mass of that compound that will be needed. Let's set this problem up. First, we have a mass of chlorine, 25.0 grams. Multiplying this by the molar mass, with the mass on the bottom to cancel grams, gives us the number of moles of chlorine. We can immediately multiply this by our molar ratio, with moles of chlorine on the bottom to cancel it out and moles of sodium hydroxide on top. The numbers of moles come from the balanced equation. Finally, we apply the molar mass of sodium hydroxide to convert that number of moles into grams. With all other units canceling, we end up with grams of sodium hydroxide, which is what we want. That gives us 28.2 grams, the mass of sodium hydroxide needed to react with 25.0 grams of chlorine in this reaction to make bleach. That was an example where we used a balanced chemical equation to find the amount of one reactant required to react with another. Of course, the molar ratios in a balanced equation also tell us something about how much of the product of a chemical reaction we can form too. Like most things in life, though, chemical reactions are rarely 100% efficient. The amount of product that you calculate can be formed via stoichiometry is called the theoretical yield. If you actually perform a reaction and weigh out the product at the end, that represents what's called the actual yield. We can compare the two values to find the percent yield, essentially what percentage of the idealized amount of product was actually obtained. If the theoretical yield of a reaction is 10 grams, for instance, and we manage to recover 10 grams of product, that would be 100% yield. If we only get 5 grams of product out, that would be 50% yield, etc.